Alright, so this is going to be Unit 4, Chemical Reactions, which is a really neat unit. It includes an excellent lab that you guys, I think, are really going to enjoy. And really, it's investigating the crux of chemistry, which are chemical reactions. So we're going to start with introducing chemical change and understanding what a chemical change is. By definition, chemical changes are any change that result in the formation of new chemical substances. So we break and reform bonds. So you have original bonds from original molecules. Some type of chemical reaction occurs. Those bonds break. The molecules or the atoms of the molecules reform new bonds, and you have new chemicals out the backside. And some examples in everyday life of this are rusting and explosions and digestion. And I've got a pictorial example here even of a rotting apple, which is a great example of chemical change. If you ask yourself, well, what isn't a chemical change? What types of changes aren't chemical? These types of changes are typically physical changes. There are any changes that don't result in a change of the chemical identity. So examples here would be like freezing, melting, and cutting. Really any phase change. Freezing, melting, evaporation, condensation. Those are all really nice examples of physical changes. So if you notice in my diagram here in the lower left-hand corner, we've got an example of a physical change. That's just taking water, original water, and now turning it into ice. The molecule's the same. It's still H2O. The water's H2O, the liquid water's H2O, the solid water's H2O. So that doesn't change. On the right side, this is a chemical change. This would be like taking hydrogen peroxide and altering that molecule to make water and oxygen. Okay, that's the two blue spheres put together are oxygen. So that would be an example of a chemical change because the chemical identity of the original substances is changing. Physical changes, that doesn't happen. We got H2O on both the left side and the right side. So, how do we represent chemical change? Well, we do so by using an object called a chemical equation, which is just simply a symbolic representation of a chemical reaction. So let's take a look here at a chemical equation, and then we are just going to define different parts of that chemical equation. So let's look at the combustion of methane. So carbon tetrahydride, which I'm drawing right now, is better known as methane. That's actually the gas that comes out of our Bunsen burners that we light. And when we light it, it combines with oxygen gas and it produces two different things. The first thing is carbon dioxide, and the second thing is water, H2O. Okay? So this is a chemical equation, a symbolic representation of what's going on. The things on the left side, so these two things right here, these have a special name. These are called reactants. So they're the things that are reacting together initially. On the right side, these things right here are called products. The products are the things that we're getting at the end of the day, that we're left with. The little arrow in the middle of the diagram here, that's got a name too. We call that the yields arrow. The yields arrow. All right. Now, sometimes chemical reactions will have some different things on them besides what I have. Sometimes there will be a symbol over the top of the yields arrow to look like a triangle. Okay, the triangle just means that we have added heat to the reaction. Sometimes that's there, sometimes that's not. Okay. Otherwise, sometimes there will be actual chemicals in the top of the yields arrow. Those usually are identified as catalysts, and we'll talk about that later on down the road. All right, now, if you looked at that previous chemical equation and you have any background in chemistry whatsoever, you may have noticed that there was something wrong with it, and that something is that it wasn't obeying the law of conservation of mass. So let me rewrite that equation and point out this strict issue. Carbon dioxide and water. So the law of conservation of mass just simply states that mass cannot be created or destroyed. Okay, it's a very important law. It's one of maybe the main focus in building laws of chemistry. And if you'll notice in this particular equation, I actually have 4 hydrogens here on the left-hand side. I got 4 hydrogen atoms. But on the right-hand side, I've only got 2. So I've done a little bit of magic here, essentially. I've made hydrogen disappear. That can't happen. All of the atoms that you start with at the beginning of a chemical equation, so all of the atoms that you start with on the reactant side, need to be located on the product side. Now, they may be in different combinations, they may be combined with something else, but they have to be present. So, in order to make that happen, we do something called balancing. We balance the chemical equation. Okay? So, some of the tricks of the trade are usually you want to leave oxygen and hydrogen to the end. Start with all the other elements first. So we have carbon being another element, but if you look on the left side, we have 1 carbon atom right here and 1 carbon atom right there. So carbon is actually good to go at this point. So now I'm going to actually go to hydrogen. So hydrogen, like I said before, we have 4 hydrogens here on the left side and only 2 on the right. So what I do to remedy that is I put a large 2 in front of the water molecule. Okay, and that number has a special name. That number is called a coefficient. Coefficient. And what that says is that I now have produced 2 water molecules. So if I take 1 methane and 1 oxygen molecule, put them together, I'm going to produce 2 water molecules. Okay, so my hydrogens now, if you look on both the left side and the right side, my hydrogens are actually equal to each other. Okay, 4 there and 2H2. So you got to kind of multiply the coefficient and the subscript, and sure enough, you've got 4 hydrogens. Now, the only other thing that is not balanced are the oxygen atoms. So let's go take a look at the oxygens. Over here, I've got 2 of them. Okay. And let's see, on the right side, on the product side, I have 2 right there, but I only have, now this is tricky, so people might say, well, I've got 1 more right there, but you got to remember that the coefficient, the purple 2 in front of the water, not only corresponds to the hydrogen, but also to the oxygen. So in fact, I have 2 more oxygens right there. So in total, on the right side of my yield zero, I have 4 oxygens, where I only have 2 oxygens over here on the left side. So in order to remedy that, I'm going to put a 2 coefficient in front of the oxygen, just like that. Now let me erase some of this side stuff and clean this up a little bit. And let's take a closer look at that chemical equation, and I think you'll notice that it is balanced at this point. 1 carbon on each side, 4 hydrogens on each side, and 4 oxygens on each side. So this is a balanced chemical equation that is now obeying the law of conservation of mass. Now, what I'm going to have you do in class often is to actually draw a pictorial representation of chemical equations. And for this chemical equation, this is kind of what the pictorial representation would look like. Now, these molecules are in 3 dimensions, so you don't have to draw that. They can be a little bit simpler on yours. But if you think about the previous equation that I just balanced, well, I had 2 oxygen molecules. So you'd want to draw 2 separate oxygen molecules and 1 methane molecule, or carbon tetrahydride. On the right side, I had 1 carbon dioxide, and I had 2 water molecules. Now, why is a pictorial representation nice? Well, now I can go ahead and count everything. I have 4 red spheres. Well, I've got 1, 2, 3, 4 red spheres, so that's good. And then I also have 4 white spheres. 2, 3, 4, and then there's 4 spheres of hydrogen right there, so that's good as well. And then finally, the black sphere is pretty simple. There's 1 there and 1 there. So I know that my equation is balanced. All right, so that's a quick introduction to chemical change and chemical reactions.